Most discussions of long-term climate variability simplify the system by dividing it into warm and cold periods. These are defined as greenhouse or hothouse climates when there's no significant global buildup of ice, no ice sheets as we see in Antarctica or Greenland today. Now, this is a little bit confusing because greenhouse is used in the greenhouse effect. This is different. This is a greenhouse climate. Here we see the Cretaceous, a peaceful day in the Cretaceous when all the plants and animals got together. Never happened like this. Now, the opposite extreme is what's known as an icehouse climate. Generally, through Earth's history, we've been in greenhouse or hothouse climates. These are perturbed or interrupted by icehouse climates that last for sometimes short periods of time, in other instances, quite long periods of time. So these are known loosely as the ice ages. Here we have a depiction of the paleogeography of the Earth during the Carboniferous. This is when much of the land masses of the world were concentrated near the equator. This speeded up weathering rates that drew down the carbon dioxide, as we'll see in the carbon cycle, and led to a lessening of the greenhouse effect. The lessening of the greenhouse effect and land near the pole, in this case the South Pole, led to glaciation on a large scale. So during the Permo-Carboniferous periods, the Earth was glaciated because of this. In an even more extreme case, we have evidence to suggest that the Earth went through two periods of what are called snowball Earth episodes. These snowball Earth episodes were driven again by the rise and fall in CO2. CO2 is reduced because, again, the continents were near the equator, and rapid weathering under higher temperature and precipitation regimes led to a drawdown of CO2 and a covering of the Earth with ice. There's some evidence that the entire world was a shiny cue ball. Now, we got out of this shiny cue ball situation by building up CO2 under the ice through volcanism. Volcanoes saved the Earth. A little more recently, when we talk about what most people consider to be the ice ages, we're discussing the Pleistocene ice ages. These include the Wisconsin glaciation, that's the most recent advance of glaciers, and the current interglacial, which we call the Holocene. Until about 70 years ago, we thought there were three other glaciations and three other intervals of relative warmth, the interglacials between. Emiliani in the 50s, with his isotope studies, overturned that. Now, when we say ice advances during an ice age, like the Wisconsin, this is the kind of Earth we would see from space once the clouds are removed. The ice sheet advanced down into the United States, into Illinois, Ohio, across Pennsylvania and New York, and equally as far south over Europe and Asia. Now, what Emiliani discovered in looking at foraminiferal isotope records from the deep sea, first of all, wasn't 4 isotope excursions related to 4 ice ages. He saw about 20. And these 20 occurred over the last 2 million years, meaning that each occurred approximately 100,000 years apart, more or less. Now, we can take a closer look at ice records. In this case, this is the Vostok ice core from Antarctica. In this ice core, we can see rises and falls in isotope values associated with rises and falls in temperature and relative concentration of various greenhouse gases. CO2 and methane are highlighted here. Which brings us to the question, what causes these glacial interglacial episodes during the Pleistocene? One attempt to solve this problem was back in the 20s by a Serbian mathematician, Milutin Milankovic, or Milutin Milankovic, as most Americans would pronounce it. What he looked at was the Pleistocene alternation between glacial and interglacial episodes and the timing of those alternations. He looked at 3 other glaciations and intervening glacial warm intervals because he didn't know about the longer-term record that Emiliani was to learn about 35 years later. What's driving all this? What is the cause of these recent glaciations? An examination of the global curve shows a periodicity of about 100,000 years. Now, that's because they've been tuned to 100,000 years. That's problematic. The same periodicity was apparent in Emiliani's work, and it led to him to conclude that the glacial interglacial cycles were due to variability in the Earth's orbital parameters. These are now known as Milankovic cycles after Milutin Milankovic, a Serb who argued in the early part of the 20th century, actually during World War I, that ice ages were caused by this orbital variability. The three parameters of most interest here are eccentricity, obliquity, and precession. So Milankovitch was a strong and early proponent of the idea of orbital variability influencing Earth's climate, but it wasn't his idea. It came about from another man named James Kroll of Scotland, and he suggested it many, many decades, a half a century before Milankovitch. He published a few papers of his own and became kind of a Scottish Goodwill Hunting. He was born on a farm, self-educated. He taught himself physics and astronomy. By the time he was 16, he became a wheelwright. And then, because of health problems, he became a tea merchant. So he ran a tea shop in Moray. In the 1850s, he managed a hotel and then became an insurance agent. And in 1859, this is important, he became caretaker at a museum in Glasgow. Important because he used his job to gain access to books. There was no internet at the time, so if you're a poor guy like he was, well, not poor, but not wealthy by any means, you need to have access to information. He corresponded with Charles Lyell on links between ice ages and variations in the Earth's orbit. This led to a position in the Edinburgh office of the Geological Survey of Scotland as keeper of maps and correspondence, where the director encouraged his research. He published a number of books and papers which were really groundbreaking, including Climate and Time in their geological relations. In 1875, he talked with Darwin on erosion by rivers. Darwin was a geologist by training. He was on the Beagle, traveling around the world, making his discoveries on evolution, at least formulating his ideas, while he was supposed to be looking for silver. So he was shirking his duties as a geologist to develop the idea of evolution. In 1876, Kroll was elected Fellow of the Royal Society, and he was given an honorary degree by the University of St. Andrews. He retired in 1880 as his health was declining further, and he died in 1890. Kind of a sad ending to a bright guy. Now this brings us to another bright guy. This is Milutin Milankovitch, born in 1879, so just prior to Kroll's death, and he lived till the 1950s, almost 1960s. He was a Serb who was homeschooled. Like Kroll, bad health kept him home. Once he began to attend high school, he became the best student in the school. In fact, he was the best student in Serbia, which was part of the Austro-Hungarian Empire at the time. But he was encouraged by his family to get an agricultural degree so that he could maintain their property, their land holdings. He wanted to study electrical engineering, but that degree wasn't offered in Vienna where he was living, so he went into bridge engineering, earning his PhD at the age of 25 for Beitrag zur Theorie der Druckkurven, the theory of bridge curves, essentially. At the beginning of 1905, he became employed as an engineer working in Vienna, and he ended up designing lots of Belgrade, Yugoslavia today. Well, Yugoslavia in the 90s, Serbia today. So he was offered a position at the University of Belgrade in mathematics. He got married. Right after his wedding, he was arrested as a citizen of Serbia and sent to prison in Karlovac, famous now for its beer, and later in Osijek. His family got him released as long as he agreed to stay away from the Serbian border. He got sent to Budapest, where he had to report to the police station every day during the rest of the First World War. While he was sort of penned away in Budapest, he devoted his time to these Milankovitch cycles. And by the end of the war, he finished a monograph that was published in 1920. It's the theory of the phenomena of the thermal characteristics of solar radiation. That's illustrated here with eccentricity being the expansion and contraction of the ovalness, or the eccentricity of the Earth's orbit around the sun. Obliquity is variability in tilt, sort of a wobble between 21.5 degrees and 24.5 degrees of tilt. And then precession, where the Earth is located relative to a specific period of time. In 2020, the Earth is closest to the sun in January. As a result, Northern Hemisphere winters and Southern Hemisphere summers are somewhat milder than they would be otherwise. Imagine that. For a given latitude and season, precession will result in about a 5% difference in insolation. While the Earth's orbit is only slightly elliptical and variations in eccentricity are small, these variations are magnified because insolation varies with the inverse square of the Earth-Sun distance. Variation in tilt approximates a simple sinusoidal function with a period of 41,000 years. Variation in eccentricity can be approximately described as having a period of 100,000 years, but really variation in eccentricity is more complex, with periods of 123,000 years, 85,000 years, 58,000 years, while variability in precession has periodicities of 23 and 18,000 years. So Mealy early on in the 1950s suspected that these variations in the Earth's orbit are going to be related to variations in the delta 18O value of deep sea sediment. Ultimately, these bumps and wiggles, these rises and falls can coincide. They can stack up. And as odd as that may seem, this is what results in the glacial-interglacial cyclicity that we observe on the Earth. Sometimes it seems crazy these would all line up at the same time, but think back at a time when there were bushfires killing 1 billion animals, an impeachment, a pandemic, ice storms that freeze states out. Who could imagine all of that happening at the same time? Unbelievable. When we look at continents, things get a little more difficult. Climate change leaves a record on continents, as it does in the deep sea, but on the continents, the complications are greater. A record may be stored as ice or carbonate precipitated from water, either in a clamshell that's deposited in sediment, or a speleothem which precipitates carbonate as water is dripping from it in a cave. We can break down this orbital variability into 3 very simple categories in the Milankovitch cycling. Eccentricity has a periodicity of about 100,000 years. Tilt has a periodicity of about 41,000 years. And precession has a variability or a cyclicity of about 23,000 years. Now, the interesting thing is the big change seems to happen about every 100,000 years, but the perturbation in insulation is minimal at 100,000 year periodicity. In other words, the other parameters, tilt and precession, are much stronger than the 100,000 year forcing. And this is what's known as the 100,000 year paradox. That means it doesn't quite work. We're not giving up, but it's looking shaky at times.
They call that a paradox.
So this climate variability extends further back into time with even larger events. The ancient ice ages, as we'll call them here, include the Permo-Pennsylvanian ice ages. We call them the Permo-Carboniferous a little bit earlier in lecture. They go by both names. The Proterozoic, snowball Earth, seems to have happened twice, about 800 million years ago and about 600 million years ago. Those are 2 key periods in Earth history for a number of other reasons related to the biosphere principally. And then we have the Ordovician Ice Age, which occurred at the very end of the Ordovician. It occurred 441 million years ago, and based on work we've done in Nevada and Anacostia Island and a couple other locations around the world, this was a double ice age that occurred about 100,000 years apart, potentially, at the end of the Ordovician, and it was sufficient to cause a mass extinction. It's the only mass extinction that has been determined to be related to an ice age or climate change. We can look at shorter-term variations, 1,000-year cycles imposed on longer cycles. Now, in a very rough sense, we can look at the current time as being warm. We can look back 1,000 years to the medieval period, another warm period known as the medieval optimum or the medieval warm period. 1,000 years before that, we're in the Roman warm period. So at least the last 3 warm episodes in human history are about 1,000 years apart. Now going back to 1,000 years BC or BCE, there's potential for a relative warm period at that time as well. So we need to consider those. We don't know them as well as the big ones, but they are important, obviously, for human history. And we can look at 30 to 50-year global variability, global periodicity, that's probably related to changes in ocean circulation. Things like ENSO that affect the Circum-Pacific region, the North Atlantic Oscillation, which affects the North Atlantic, the Pacific Decadal Oscillation, which affects the Northern Pacific, operates on about a 30-year cycle. The North Atlantic Oscillation around, let's say, 7 years. El Nino, 3 to 7 years or so. Occasionally these things line up, just like the orbital parameters in Milankovitch cycling. When they line up, they might flip the switch. That's called the flickering switch of climate. You flick it on to warm, you flick it off to cold. That may happen at these periodicities because of changes in ocean circulation. This brings us to the carbon cycle. It's one of the main drivers of climate variability in the modern world, in the human world, in the Anthropocene, as we call it. Carbon dioxide levels in the atmosphere have varied from around 275 parts per million before the Industrial Revolution That would be looking back to the 1840s or so. We managed to go from 275 or 280 up to 370 in about 150 years to the year 2000. And I'm going to estimate that in May of this year, we're going to hit 420 parts per million. So you can write that down. If I'm wrong by more than, let's say, 3 parts per million, I'll give everybody a bonus point. However, the carbon dioxide in the atmosphere should be higher. The amount should be greater than it is. Something is therefore removing that carbon. That was one of the focal points of my master's thesis in the Florida Keys and the Bahamas. Where is the carbon going? It turns out a lot of it is probably going into shallow seawater, and once it reaches pore fluids, the water between the little grains of carbonate material that make up the white sands of the beach and the white sediment offshore, it dissolves that calcium carbonate. So we're dissolving calcium carbonate to remove some of the CO2 from the atmosphere. Eventually we're going to hit a limit on that. The brakes are going to be applied and the ocean's no longer going to be able to take up this extra CO2. So this brings us to geochemical cycles and the way they work. We'll start out talking about geochemical reservoirs. This is a place where a substance goes and stays for a period of time. That period of time is known as the residence time. And what changes the residence time, what changes the input or output of a reservoir is potentially a chemical reaction. It could be physical, but it also could be chemical. And this is going to result in, ultimately, a transport across interfaces to reach equilibrium between systems, between the atmosphere and the ocean. Right now, the atmosphere has more CO2 than the ocean, so the net movement is CO2 from the atmosphere into the ocean, dissolving calcium carbonate. So here we see an example of increased carbon dioxide in the atmosphere, leading to acid rain and ocean acidification. This is something we talked about briefly earlier in the course. Okay, let's burn some stuff and see what happens. Starting out with the consumption of fossil fuels and burning, say, forests and flaming landfills, we generate carbon dioxide that is going to move away from the source of the burning in the atmosphere. The CO2 is going to mix with water vapor, forming carbonic acid. This carbonic acid is going to dissociate into bicarbonate and hydronium ion. This hydronium ion can in turn join a carbonate and become more bicarbonate. Or this carbonate can join up with a calcium ion and become calcium carbonate. This gives off CO2. So the accumulation of CO2 here in the form of calcium carbonate is something that can move along the ocean basin, with the net effect being reduction of carbonate available to marine organisms that precipitate calcium carbonate. So it's changing the budget. It's making it more difficult for calcium carbonate producing organisms to be themselves, to produce the hard parts that become ultimately limestone or dolostone. In this diagram, we see the big budget picture of CO2. The atmosphere contains 830 gigatons of carbon. The ocean, 38,000 gigatons of carbon, so much larger reservoir. The reservoir in carbonate rock and organic matter that's stored as fossil fuels and just simply stored in rock is much, much greater. So we're going to take a cursory look at that for now. It's covered in more detail in Geology 206 Earth System Science. In photosynthesis, we have an exchange between the atmosphere and the biosphere. We're transferring inorganic CO2 in the atmosphere to organic matter made up, in this case, in the form of plants that break down into soil organic matter, which is another large component of the carbon budget. So this material in the land, this carbon that's stored in the soil, can end up as fossil fuel, or it can be remobilized, it can be respirated, it can be turned back into inorganic CO2 by microbes. Weathering is going to remove about 0.2 gigatons per year. That's the dissolution of carbonate rock and silicate rock to a lesser degree. That's going to release carbonate and bicarbonate ions to the ocean during that dissolution process. Volcanism contributes very little to the carbon budget annually. It's a tiny little puff of CO2 compared to what humans are doing. And as a result, it doesn't really play into our climate change models. Now, the big exchange is going to be between the air and the sea here. 80 gigatons of carbon is going to move back and forth between the surface ocean and the atmosphere. The atmosphere has a lot less CO2 than the ocean, but its equilibrium concentration can be greater. The net drive is for that CO2 to come out of the atmosphere, out of the gas phase, and dissolve into the ocean, where it can be picked up by phytoplankton and turned into organic matter, or it can be converted into sediment. Ultimately, if this sediment persists, it can be recycled at a mid-ocean ridge or in a subduction zone. Now, humans add CO2 to the atmosphere. We do it in a variety of ways. We do it as a result of the burning of fossil fuels, deforestation, we make concrete. All these things add carbon to the atmosphere. Plants and the air-sea exchange between the atmosphere and the ocean removes some of it, but in spite of that, there's a net annual increase. So what we're doing is releasing a total of 8.9 gigatons of carbon into the atmosphere each year. 7.7 of that comes from the burning or consumption of fossil fuels, cement production, about 0.1 gigatons per year. Land use change via deforestation and agriculture results in an input to the atmosphere of about 1.1 gigatons per year. This is really significant, and it's seldom mentioned. The net uptake by new plant growth is 2.6 gigatons per year. We need to be careful here because this 2.6 gigatons a year comes out of the atmosphere, goes into the terrestrial biosphere, and a lot of that decays and goes back into the atmosphere. So the net change is insignificant or even negative. The ocean uptake by air-sea gas exchange is about 2.3 gigatons per year. This CO2 is dissolving in the surface oceans, where ultimately it's going to dissolve carbonate in shallow water platform settings. The net increase, the net budget, is that we're adding 4 gigatons a year to the atmosphere that's not being removed. That's a problem. So the result is, over the 20th century, we can see that because of our fossil fuel burning, deforestation, we've dramatically enhanced the greenhouse effect. That's observed here in some ice cores, such as the Vostok ice core, where we have a measure of the isotope value of the oxygen and hydrogen that make up the ice. We also have concentrations of greenhouse gases like CO2 and methane that we obtain from little air bubbles that are stored or locked in this ice. So we see the rises and falls in temperature coinciding roughly with the rises and falls in the concentration of greenhouse gases. Now, this is what the ice coring operation looks like. At least it did look like this in the 80s. A little bit more sophisticated now. Not much, but a little bit. If you're interested in a job like that, there are jobs like that. In fact, this was just announced the other day. 15 PhD research positions in ice core related climate science are available within the Deep Ice Project. I'll let you read this in your spare time. Here we have a diagram that illustrates the 20th century warming, 20th century change in temperature. Going from 1850 to 2000, we can see the CO2 concentration here in this blue line, rising roughly in concert with the change in temperature. Now, temperature is a little wilder in some respects, and this is also relatable to human activities. You can see the temperature rising up to the late 40s, kind of leveling off, and then plunging in the late 40s to the late 50s or so, and then again in the 60s and 70s. And what was happening here is temperatures rising as CO2 is rising, but then we increase our coal power plant activity. We inject lots of sulfur dioxide in the atmosphere. It acts like a mirror, reflecting radiation back into space, cooling the atmosphere and generating acid rain. So we stopped doing that. We scrubbed the SO2 from coal power plant stacks. The sky cleared up and the temperature went up. That was unfortunate. Now, if we look back further in time, from the year 1000 to the year 2000, we can see again that CO2 concentrations roughly correlate with temperature. This temperature, I can go on forever about what's right and wrong about it. It's known as the hockey stick because it looks just like a hockey stick, I guess, to people from Pennsylvania, which is where I think it was coined, Penn State. So again, there appears to be a correlation between CO2 and temperatures. Again, focusing on the 20th century, we can see a rough correlation when we take into account other things we're doing to the atmosphere, such as the sulfate aerosols. We can account for these oddities.